Hello, everyone, and welcome to Talk Nerdy. Today is Monday, August 19th, 2024, and I'm the host of the show, Cara Santa Maria. And as always, before we dive into this week's episode, I want to thank those of you who made Talk Nerdy possible. Remember, the show is and will always be 100% free to download, and the way that we keep the train on the tracks is by relying on the support of individuals just like you. The platform that I use is Patreon, Patreon. And if you are interested in supporting the show, you can visit patreon.com/talknerdy, and you can pledge any dollar amount at all on a per episode basis. This week's top patrons include Anu Bharavaj, Daniel Lang, David J.E. Smith, Mary Neva, Rika Maharaj, Brian Holden, David Compton, Gabrielle F. Jaramillo, Joe Wilkinson, Pasquale Gelati, and Ulrika Hagman. All right, let's get into it. So this week I had the opportunity to chat with Dr. Sara Imari Walker. She's an astrobiologist and a theoretical physicist. She's the deputy director of the Beyond Center for Fundamental Concepts in Science and a professor in the School of Earth and Space Exploration at Arizona State University. She's also, this is really interesting, I love this, the co-founder of the astrobiology-themed social website SaganNet.org, so SAGANET.org, and she's a member of the board of directors of Blue Marble Space. So Dr. Walker is most interested in whether or not there are laws of life related to how information structures the physical world that could universally describe life here on Earth, but also on other planets. And that's the topic that we're going to be diving into as we talk about her new book. It's called Life as No One Knows It: The Physics of Life's Emergence. So without any further ado, here she is, Dr. Sara Imari Walker. Well, Sara, thank you so much for joining me today.
I'm really happy to be here.
So we're going to be talking about your new book and also your work and just all things curious and interesting. Life as No One Knows It: The Physics of Life's Emergence. And wow, what a big topic. We have kind of touched on aspects of this in the past on the show. I mean, we've now been on the air for like over 500 episodes, so we've sort of bumped up against, but maybe not so much from a physics perspective, more from like a biochemistry perspective. But before we get into this, I want to learn a little more about you, about your kind of path and your journey and your interest area. So, okay, you're the deputy director of the Beyond Center for Fundamental Concepts in Science, and you're a professor at Arizona State University in the School of Earth and Space Exploration. How do you define yourself? Are you a physicist? Are you an biologist? Are you more theoretical? Are you more experimental?
Yeah, I think all of the above.
Oh, nice. Love it.
I mean, it's really hard to define yourself when you're actually defined by a question, not a discipline. So I'm really just interested in answering what life is. And my philosophy has been, really answering that question to solve the origin of life. Like, that is the origin of life. You have to use whatever tools you can find and whatever things you want to throw at that question. But formally, I'm trained in theoretical physics, and I do identify as a theoretical physicist because of the way that I think about and approach problems, which tends to be like my deep core interests, like who I am intrinsically as a human being, is very passionate about fundamental understanding of reality and what that means, and where we might find new insights to understanding the way the world works better at like the deepest levels of explanation. And so I'm fundamentally interested in the problem of origin of life because I think it's really that frontier for physics. So in practice, I'm an astrobiologist because the origin of life is part of the field of astrobiology. But I'd say what I do is very much the sort of art of the practice of what it is to be a theoretical physicist, which is really, trying to come up with new theories and new ideas to broaden the explanation of things that we understand in nature.
I am so excited about this topic, especially, and like just the way that you've sort of dedicated your career to investigating these questions. I think that when I think back to episodes of Talk Nerdy in the past where we've brushed up against this question, I often pushed it in the very direction that you're describing. I think back to like Dr. Mike Lee, Dr. Kevin Hand. I've had a few astrobiologists on the show where we talked about their specific foci. Like, okay, we're going to talk a little bit about Europa and what kind of promise Europa holds, or we're going to talk about viruses, or we're going to talk about definitions. But I'm most it's interesting. I'm most reminded of a series, not a series, but two episodes I had with Alexa Miller and Lulu Miller. Lulu Miller is one of the Radiolab hosts, and Alexa Miller is, interestingly, her sister who teaches about art and medicine. And both of those episodes, we really grappled with the topic of like categorization and constructs, and just sort of the way that we as human beings like to uh, lump and split things to make sense of the world, but that those are really not. There's nothing fundamental about them. They're purely um, uh, constructed in order for us to make sense of how we navigate the world. And I'm curious, is this an area that you spend a lot of your time kind of thinking?
Yeah, I do. I do because I don't really, as I already said, I don't really identify with a specific discipline, although I identify with my training, right? So I understand how I was trained and how I think and how I want to think. But I think some problems really defy what would be considered traditional disciplinary boundaries, and not even in the way that they're interdisciplinary. Like interdisciplinary is, merging two existing disciplines to ask a question at the boundary of them. But it's almost like there are some problems that are just like beyond any discipline that we've yet defined, because disciplines are really, they become constructed out of the ways historically we've come to know the world and the way that we want to partition that understanding. In nature, it's not really, nature doesn't make a distinction necessarily between chemistry and biochemistry, but we make a distinction because of where we happen to find certain molecules. Um, so I think, I think that that kind of thing is really important. And I have always really felt in my field that, the ways that we were asking the question of the nature of life didn't really do that sort of tunneling through the disciplinary training enough. So in astrobiology, we have a lot of people that study astrobiology as a discipline and are asking questions about like, is astrobiology a discipline yet? Which I think is a really funny and interesting question. But it's a really relevant question because almost everybody that comes into the field of astrobiology was trained in a different discipline. There's very few programs, for undergraduates to study astrobiology as their major. Actually, ASU, where I work, is one of the few institutions that has an astrobiology major. And when I started my career, there were no astrobiology majors at any institution, at least that I knew about. So it's a very new sort of area, and it's a merger of a lot of different areas. But, one interesting question is, will astrobiology become its own paradigm? And what would it look like if it had its own paradigmatic approach and it wasn't borrowing methods and tools from other disciplines, but it actually invented it its own? And in some sense, that's what you might call a mature discipline. And astrobiology is not there yet. And I do talk about in the book a little bit about what I think some of that transition might look like. But that's one of the reasons I find the field really exciting, is because it's one of the places where you really get confronted with the fact that nature doesn't draw the boundaries that we do.
Yeah, and it's nature doesn't draw the boundaries that we do. I mean, even a question as simple as like, what is life? And how does life emerge? And would we recognize life if we came across it in some other context, right? Like we often talk about how we have an N of one. Like here on planet Earth, we know what life is based on how life evolved here. And we don't even fully know, but we think we know. There's still questions about what happened right at the beginning. But we have all these definitions of life, but even still, like people grapple about like, ooh, is a virus alive? Is this kind of like thing, like how does a parasite fit into that question? And then now we're opening this up into, would we even know life elsewhere? So I'm super curious. Did you find this question in your physics pursuits? Like as you were training in physics, did you start to become more enamored with this question? Or were you always interested in answering questions about the fundamental nature of life and you chose physics explicitly as a path to do that?
It was totally the former. So um, I my parents didn't go to university, and they're very artistic. So like my dad's a hairstylist and my mom is an antique dealer. And so I didn't, they're very intellectually curious people, but like, science wasn't like the thing in my house. And, so it was very fun. I like, had a very creative childhood, but I didn't really, I liked science in high school, but I didn't really know that I loved physics until I went to community college. I went to community college because I didn't know anything about university. And I was like, okay, what do you do when you don't know about university? So I went to Cape Cod Community College. It was an amazing experience, but I had some really fantastic professors there. And I just took all the science classes and I just absolutely fell in love with physics. I don't even know like how to describe how transformative it was to me to be like my first week at school there sitting in a physics class and just really like feeling like I just like knew that I wanted to do physics. Um, and so I think what really struck me about physics as a way of understanding the world was how the human mind can come to understand these deep regularities of nature and like actually make predictions about things that we don't even understand or could exist yet. And so I really wanted to do that. I really wanted to contribute to theoretical physics. So at like 18 years old, I basically decided I wanted to be a theoretical physicist and whatever that looks like. And I even remember telling my physics professor that I was, like my aspiration was to win a Nobel Prize in physics, and him kind of laughing and being like, well, so, like that's kind of a big goal, Sarah, not in a bad way. So like, sometimes more discouraging, not in a bad way. But I remember telling him that I actually didn't want to win a Nobel Prize. I just thought that was a good goal to set because it meant if I like could get to that level, I was really doing theoretical physics and I was really contributing something deep to our understanding. So like at 18, I knew that's what I wanted to do. But it wasn't until I was at graduate school. So I went to undergrad and in Florida Tech, and I joined a particle physics group, and it was experimental particle physics, but I really knew I wanted to do theory. And so when I got to my PhD in Dartmouth College, I wanted to join the cosmology group because I thought, like the most fundamental things you could study, were the earliest stages of the universe. Like how did the universe even come to be? And particle physics, like the most elementary stuff we're made out of, right? And this is like what you'll hear about in, classic, popular science communication about theoretical physics. Like these are the foundations. This is like the stuff the universe is made of. And these are the biggest questions. And so I was like really gung ho on that stuff. And, there were like 10 graduate students that joined the department at the same time. And 8 of us wanted to be cosmologists. And I was like, oh my God, how am I going to like do this? And there were only 2 professors that worked in cosmology in my department. So it was like, everybody wanted to work with them. But my PhD advisor, Marcelo, who I ended up working with, one of the things that he was trying to get someone to do was think about astrobiology. And so he's like, Sarah, you want to work on this problem in astrobiology? I was like, sure, I'll take it. And I was thinking at the time, I was like, oh, I'll do this and I'll get to go back to doing cosmology. And so, so anyway, long story short, I started working on a particular problem, the origin of life, which is related to the origin of homochirality, like why, the amino acids and proteins are left-handed when they can come in a mirror image right-handed form, and sugars and DNA are right-handed. And I was working on that problem for a little while, but as I was reading more and more of the origin of life literature, I realized how open the question was, and that nobody in the field really knew how to ask the question of the origin of life. And in fact, people were avoiding it, which I found really shocking. So most of the literature in the origin of life I was reading and most of the conferences I were going to, people are talking about prebiotic synthesis, like making a few amino acids under abiotic conditions or a few nucleotides, or people were also trying to retrace back to the last universal common ancestor. But there's a huge gap in complexity between making like simple molecules in a prebiotic environment and having a fully functioning, ancestor to all known life on Earth.
That's true. And I think we often don't think about that. We think about like, oh, all this stuff is spontaneously, like maybe with some electricity or something, going to combine, and somehow life will just sort of emerge, like self-assemble and emerge. And I
Yeah.
think we see things now, like these really interesting examples where if you throw a bunch of neurons into a dish, they like grow into something that we recognize, and that there are these sort of plans, and there is this kind of self-assembly or this spontaneous. But no, that's very complex. Like that's evolved over millennia.
Right. Yeah, this is a super important observation. And I think you're exactly hitting on the point that, is often missed. Like those neurons are the product of billions of years of evolution. The petri dish is the product of technological infrastructure that also required millions of years of evolution. So you're putting a ton of boundary conditions in to see this emergent property in a petri dish. Right. And all that information is contingent on the history of life on Earth and the information that's been acquired over billions of years. And the origin of life is critically hard because you start from nothing, like literally nothing. There's no pre-planned anything. It's just random chemistry. And the problem is incredibly hard for that reason. And this idea of looking at the transition from non-life to life is really hard. So what I had found was that most people in the field were avoiding it in favor of easier questions that were things that, could be answered
Mm.
on a time scale of a PhD, which is totally reasonable. Um,
Yeah.
but I really wanted to think about a hard question. And so I became really enamored with this idea of thinking about the origin of life and whether physics and the perspective of a physicist could contribute anything new to it. And it really fulfilled for me the long-term interest I had in like being really like, romantically enthralled in some way with like the history of physics and the amazing ideas that had come out of them and the deep abstractions, and really wanting to contribute something new to that story. That origin of life was a territory where there was some chance of that happening. It's probably a low chance because it's a super hard problem, but at least it was worth risking my career on to try to work on this problem. So that's when I started working on it. Yeah.
What was your approach? What specific questions did you ask, and what were you able to kind of it's hard, right? Because when we're doing a graduate, like a doctorate level research project, we do have to be constrained to some extent, like you mentioned, so that we don't take 15
Yeah.
years to
Yeah.
finish. So it's like you want to do something that shows something so that then for the rest of your career, you can continue to work on
Yeah, yeah, exactly. I think it's super important, especially like, for any graduate students listening, to pick tractable problems. Like you don't have to pick the biggest problem of your career as a graduate student. And I have to tell this to my PhD students all the time, because of course they want to come and work with me because we work on big questions. But I'm like, you don't have to answer all the questions right now. You just have to answer a question or even a part of the question. So for me, what that looks like is I did my entire PhD on chiral symmetry breaking. So this idea of like, how do you get left and right-handed molecules to, like select one over the other in a chemical reaction network, and what role might that play in the origin of life? So I worked on that. It's a nice problem from the perspective of physics because it's mappable to spontaneous symmetry breaking. And that was all really fun. But at the same time, I was reading all this literature on the origin of life and really confronting, all the hard questions associated with it. So what ended up happening is, by the time I was ready to finish my PhD, I was pretty convinced that the main difference between the way that we talk about physics now and sort of all the current theories of physics that I had studied through all of my education, and the way that life was described was information plays a really critical role in living matter, and information doesn't play a fundamental or really critical role in physics. And obviously you can describe information in physics, and there's different ways that it pops up in different sectors of physics, but it's not a fundamental category of nature, and it's usually used in more of a descriptive sense. But in biology, it seemed to be really fundamental. And so by the time I finished my PhD, I was just pretty adamant that what I wanted to do was try to understand what was the role of information in the origin of life, and was there some way of formalizing the origin of life transition in that framing. And so that's sort of how I got on it. And that's basically how I framed the question my entire career. But it's evolved quite a lot into this new theory that I'm working on, which has really different properties, but I think answers all the questions that I was struggling with all those years.
So I guess help us understand a little bit, as I'm assuming many of the listeners are non-physicists. I am a non-physicist. I'm a psychologist, so I come at these questions from a wildly different perspective. What do you mean when you talk about the role of information specifically? Like what forms does information take within your sort of contextual frame?
Yeah, so it's very different for me now than it would have been as I described it early in my career. So, sort of the main sort of way that I started approaching the problem was to think about the fact that information, which is a really abstract thing, seems to have some causation in the world. So like you can think about the words I'm speaking right now even as information. And it's really weird if you think about it. The fact that I'm articulating something that carries meaning, I'm speaking it into a microphone right now, and all the listeners out there are going to be hearing this information. And I could say something like and there's an experiment like this in the book, but like, I like maybe jump up and down, right? And like maybe some of you will jump up and down, right? So what is it about the information that actually caused that event to happen? I have no idea what other events in space and time like this conversation is going to cause to happen because of things that we might say now. So information has a kind of like disembodied property, and it also is true even in the context of the cell. People will make these kind of debates like DNA carries information, but of course take a DNA molecule outside of the cell and you just look at the sequence of AGCs and Ts in it, you basically you can't tell the difference between a DNA strand that carries function and one that doesn't just based on the sequence alone. So there's some sort of contextual property, some property that seems more abstract about the nature of information, and philosophers and scientists have struggled with this for decades, if not, millennia in some sense. And so, it seems to come up right away in any kind of conversation you want to have about the nature of life, that there's this property that we want to call information. We don't know exactly what it is. You might call it causation. You might call it context. You might just call it complexity. But people haven't had a sort of rigorous way of quantifying that. And so I was really interested in this concept of top-down causation, which is the idea that thoughts can actually, they're very abstract, right? Like, what is a thought? How much does a thought weigh is like kind of a weird question, because it's like, it's kind of imbuing physical properties to something that, we don't usually think of as physical, but it has physical impact in the world. And, there's no room in standard physics for thoughts to have causation. And so, there's all those are just a few examples, but there's all these perplexing cases where, it seems very inconsistent with our current narratives in physics. There seems no natural path to reconcile that information has physicality to it. And therefore, sort of the standard approach is just to assume it's an epiphenomena or it's not really real. It's not fundamental in any way. And I just wasn't satisfied with that.
Right. Like, just because, well, I guess I often, and maybe this doesn't translate or maybe it does, but in psychology or at least in neuroscience, and when we talk about these early debates about consciousness or thought, and kind of monism versus dualism, blah, 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 blah. I think the most accepted, although I don't want to speak for everybody, view is that like thought is an emergent property of brain. Like, it's not necessarily measurable through these classical tools. Like you said, it doesn't have weight, it doesn't have mass. But it also could not exist without brain activity. That an emergent property is, I think, still fundamental, but it's not measured the same way, I guess you could say.
Yeah, I think the point on measurement is really important. And so this is actually something I've been playing a lot with, and having lots of fun both in the philosophy and science. It's like literally one of my favorite intellectual playgrounds right now, is to think about measurement and what measurement means. Because, exactly as you're saying, we think about things like, weight or, electric charge or mass or things as physical, and things like thought, because we can't measure them, is not physical. And we forget that historically, everything that we think is physical, we had to evolve measuring devices that allowed us to actually reliably measure that feature of reality. And it was only after we learned how to measure it that it became a feature of our theories of physics. So I think this idea of thought being not measurable is maybe premature. It's probably that we're not, it won't capture all the things that we're talking about thought right now, maybe, but there might be, a theory of consciousness, if people get there, a theory of thought, which are two different things potentially, but that actually has measurable consequences. It's just we haven't figured out how to measure that feature of physical reality yet.
Totally. Like, I even think about, again, and I'm super curious how you process or how you contextualize this within your frame. But like, for my dissertation, which I defended recently, I interviewed people who were, thank you. Thank
That's
you.
okay.
It was horrible. No, I'm very glad. I'm very glad to be done with it. And
Yeah,
it
of
was a
course.
fascinating experience. I learned a lot. So I interviewed people who are choosing to die with medical aid. I live in California. I work in, healthcare psychology, health psychology, and I'm very interested in this concept of medical aid and dying. But I chose to do a qualitative as opposed to a quantitative dissertation because the questions I was asking would not make sense quantifiably. I did not want to hear from these people, you know, is this how you feel about this? Is this what you think about this? And then put them together in a table that said, 70% of people have existential distress when they are experiencing thoughts about death. I wanted to hear the data qualitatively. I wanted to know what their thoughts and feelings were. And in a way, is that not a measurement of thought, even if I'm not weighing it?
Yes, 100%. I totally agree with that. And I think there's kind of a misunderstanding that every measurement has to be quantitative. I stand on that side myself just because of the questions that I'm asking. And, I think we need a formal approach to life that has measurable consequences in order to say we solved the origin of life, because you need to go in the lab and you need to measure that something originated. And so, like, for me, the quantitative measurement matters, but there's a lot of things, especially when you're talking about life and meaning of life, and perceptions of life, that are much more qualitative. And I don't think that they're worth putting a quantitative assessment on.
And does that position within like a physics or even a multidisciplinary department that has a lot of like physics emphasis, does that go over well? Like how accepting
Um,
are these fields of
I
talking
don't
about qualitative data within a field that is historically been so quantitative?
I think if I was worried about whether things would go over well, I would have picked a totally different career trajectory and I wouldn't be me. I think my philosophy of doing science has always been to try to think about questions I'm really interested in, think about ones that are conceptually hard, because that's where I find my creative energy, and also try to work in spaces where there's not a lot of competition so I have time to think. And if I come up with like radical, provocative things, like they seem logical to me. So I'm happy following things that I think are logical and rational and might lead to more productive ways of asking questions and more productive answers. So there's been plenty of people that have been upset about various things I've said throughout my career for one reason or another. It's usually, actually, in my opinion, it seems like it's usually because it's confronting some dogma that they didn't realize that they had. Um, and I think that's probably the case that you're also pointing at. Like, if you're trained in the quantitative sciences, you kind of have some superiority complex about, quantification is like absolutely necessary to be, talking anything intelligent. And, that's not true. And we know that's not true. But our training, it really instills in us certain perspectives of things that sometimes are really difficult for people to question. Um,
Yeah. Yeah, no, it's true. I mean, it's interesting even in psychology, which we think of as being more kind of in some ways accepting to that, like there's whole journals that are qualitative in nature. There are whole groups of people that are like, yeah, this isn't science, which is I guess a little disconcerting. And so
yeah,
I'm super curious as somebody who has put in the effort and who is actively working to develop a a theory, and maybe we can take a minute to talk about what a theory is in science first, but like
sure.
who is really working um to make these hypotheses that are taking in information from lots of different questions to develop a sort of um a way to describe something that is new. I would love to hear, I'd love to spend adequate time in our conversation to talk about what assembly theory is, what it isn't, what questions are still very open for you, and what you feel, like you feel a little more confident about. Like, what are you, like saying, I can assert this, I think, at this point.
Yeah. Yeah, it's interesting. I mean, that changes on a daily basis, which is the fun part about science. So I like changing my mind. But and also being convinced, like, by good arguments. But I think, just for the listeners, to know a little bit about the ideas we're working on. The sort of key conjecture of assembly theory is that life is the only mechanism in the universe for building complex objects. So complex objects are things like cell phones, people, DNA. Anything that basically looks like it has design. This is always sort of the Paley's watch mystery, thing, like about evolutionary design and that whole debate. But it's hard for us to understand that like some of the structures on this planet can only exist on this planet because life is on this planet, in fact, most of them. So the key conjecture is that those things only happen because of life, and the mechanism of generating complex objects is life. And this is very against the grain of standard physics, because standard physics would say that any object can fluctuate with a small but finite probability into existence at any time. If you think about like thermodynamic fluctuations or quantum fluctuations, there's always built in this sort of low probability for very, very improbable things. And assembly theory says, no, improbable things are actually not possible unless you have a history of evolution and selection constructing objects that can construct other objects. And so some things cannot come into existence without the time and the other objects that actually have some information about how to make those objects. It seems very obvious from our day-to-day experience that might be right, but it's very radical from the perspective of a theory of physics, because it basically says evolved objects are contingent on a particular historical trajectory, and they actually have built into them the information necessary for their construction. And in assembly theory, we talk about that information in terms of the assembly index, which is sort of a stepwise procedure of building objects. You take, like if you think about a molecule, you can look at the atoms in the molecule and you can put them together to make a bond, and you can take pieces of molecules and try to construct your final molecule. It's usually easier for people with Lego. So if you think about Lego building blocks, sticking them together, and like maybe you want to make a castle, you can reuse parts you've already made. What's the shortest way that you can get to the castle? For most complex objects, that shortest path is very long, even for molecules. And it represents the amount of informational constraints necessary to make that object. It's really crazy that what you can do with that then is actually go and measure sort of evolutionary complexity in molecules in the lab. So this was something that was really developed by my collaborator, Lee Cronin, which is this idea that we can actually measure this assembly index with a mass spectrometer. And this conjecture we have that life is the only thing that can build complex objects comes with it an idea that there should be a boundary in complexity above which you only find objects if life was there to make them. And so we were able to test this because we can measure this property in the lab. So this is why measurement is important in building a theory of physics, as we were going back to like mass, wasn't a thing, or temperature wasn't a thing until we really figure out how to measure it and measure it in a standardized way. Assembly index is a measurable standardized measure for complexity of molecules. And what we found is if you look at non-living and living samples, you find that living samples are the only ones that produce molecules above a certain assembly index, which is about 15 for the experiments we've done so far. So 15 steps doesn't seem like a lot, but it's an exponentially growing space. So it's actually huge. Chemical space is huge. If you look at the Hubble field and you think the universe is big, like you should just go into a cheminformatics database and think about and like look at how many molecules people have predicted, and like the universe doesn't have enough resources to even explore all small molecules, which just blows my mind every time I think about it.
And so what you're talking about then are the small molecules that are found within living entities?
No, well, they could be potentially within living entities, but if you wanted to look at the size of chemical space, there's a few like good analogies we give. I think my favorite one is to think about the molecule Taxol, which is it's like a molecule made by I think the yucca, I don't know how to pronounce it, tree, and it's an anti-cancer drug. Its molecular weight is 853. It's not that big a molecule, but if you wanted to make one molecule for every structure with that molecular formula, it would fill 1.5 universes in volume with one molecule per centimeter cubed. So basically, like one molecule, just if you wanted to iterate all of the structure of the formula, would fill 1.5 universes.
Yeah, that's insane.
One molecule. Yeah. So this is kind of part of the point of assembly theory is that space is so huge. The universe cannot exhaust that possibility space. So what it does is evolution and selection kick in, and certain objects are constructed and others aren't. But the way to build into the space of complexity is to build on the things that have come before, because there's no way of exhausting all possibilities.
Right, because they're not starting from scratch every single time.
Exactly. And so this is why evolution occurs along lineages, and biological objects are all related to each other because they have to be, because it's the only way they can exist.
And so what about things that are not living? I mean, I know we're getting back to that more
Yeah.
philosophical question, but things
Right.
that are not living but are either remnants of things that once lived. Like, I'm thinking, we've got plants, we've got animals, we've got bacteria, we've got all this stuff, but then we've got things like rocks. And
Yeah.
rocks are really interesting because rocks are like geologic material that often contain remnants of living things, and they are also sort of built on these very long time scales and very often built upon previous structures. Like, there is a lot of complexity in things like crystals, for example, but are they
Yeah.
still not nearly as complex as the molecules found within living organisms?
So I wouldn't want to make a direct comparison between them,
Mm,
because you're actually comparing different structural spaces. So
mm-hmm.
assembly theory allows us to like kind of formalize a notion of complexity that's very physical, because it actually is, in some sense, the shape of the object when you want to actually talk about how hard it is for the universe to make it. And, I had like some of the more, deeper philosophical things that I am really excited about with the theory are like the fact that it suggests that objects have a size and time. So evolved objects actually, like the materiality of the object is this, this size about like how hard it is to construct them or assemble them. When you build that space for molecules, what that kind of assembly space looks like is really different than the structure of the space when you build it for something like a mineral. So they wouldn't necessarily have the same boundary for life between these two different materials, nor would, like you say, like if you look at like a language, like on a computer or like a human language, the boundary for it being unevolved select structure in terms of like the combinatorial space that languages could be generated out of is probably a different boundary than it is for chemistry. And so part of what I'm really interested in right now is taking this idea of, we have a measurable property, we can go in the lab, we can say these structures are definitively ones that wouldn't exist in the absence of evolution and selection. So they are parts of whatever living physics is, like living physics being sort of the set of all complex objects that the universe can't just generate spontaneously, but has to take time and history to make. And you can actually talk about a boundary in any combinatorial space above which it's necessary to have what we would call quote unquote life, or the sort of fundamental physics of evolution and selection to generate those structures. But where that boundary is depends on the physical material.
So, what are the kinds of things that fall below the boundary?
So below the boundary is things like methane, oxygen, phosphine. I mean, like canonical, like atmospheric gas biosignatures are below the boundary. I guess I'm like saying all atmospheric gases. I don't know why. It was an exoplanet morning. So, simple molecules for the most part. And, some amino acids like glycine is below that boundary. Alanine. Small molecule space is below that boundary. So these are things that you'll find, for example, in meteorites. And the reason you find them in meteorites is because they're really easy to make, and they don't require a lot of constraints and a lot of specific information to create them. And so that's the sort of thing that you find. So if you imagine if you had, like a tray of Lego, and you were shaking the Lego tray, just by some random fluctuations, or like stick your Lego in the dryer. I actually saw somebody do this on Twitter because they were trying to do assembly theory or something. I don't know. It was very funny. They tagged one of us assembly theory. It was very funny. But like, you stick Lego in the dryer and you might get some really simple structures. Those are low assembly structures, right? But you're not going to have Lego Hogwarts, spontaneously assemble in your dryer. It doesn't matter how long you run it. If you put all the pieces of Lego Hogwarts in your dryer, it's just not going to happen. And so there,
right.
So,
this is like a monkey typing on a typewriter is not going to come
exactly,
up with Shakespeare. Yeah.
Right. Except there are no monkeys. And we have to explain how these things actually come into existence besides just being spontaneous and random. And obviously we have theories of evolution, and they're great when you're studying biology and you already have an evolutionary architecture like a cell. But the question that assembly theory is trying to address is, how do you get there when you have no evolving system to begin with. How does the universe select for evolution? So that's really the fundamental question we're asking, is like looking for a structure that's deeper than genomes and deeper than the cell, that allows you to talk about evolution and selection and how these properties that then lead to these things that are actually, sort of exponential engines of evolution. A cell is a really good evolutionary architecture, right? But it had to also be invented by evolution. And so we can't fall back on sort of the standard paradigms in biology, because we don't have any replicators, we don't have any metabolism, we don't have any cells.
So I guess I was a little bit confused, and maybe this has helped to clarify that really it's not just about living things here. It's about the ingredients or the building blocks or the complexity that allows for living things, but also allows for other things that are non-living within the context of life.
Right. So I think this is also a really interesting point, that, a lot of
Mm.
people approach the problem of defining life by trying to say, this thing's life, this thing's not life.
Right. And then let's count backward and see what's different
Yeah.
about them.
And of
Yeah.
course, that leads to all the paradoxes of like, how do you define viruses? Are they alive or not? And, all the canonical debates that people have had, for ages about, trying to draw a hard boundary around the nature of life. And as we were already talking about, hard boundaries in nature are not really there, right? And so if you're actually looking for the deepest descriptions in nature, they don't have hard boundaries. And one of the things that I started to notice when I was really thinking about this problem and really thinking about the history of physics, is most of the major advances in physics have come from unifications of things that seem totally different: electricity and magnetism, space and time, wave and particle, terrestrial and celestial motion, right? So, like, every major advance in the history of physics has been unifying things that we thought were different. And the original life sits at the boundary between what we want to call life and what we want to call non-life. We need a theory that's deeper than both of those things in order to solve that transition point. And so it really requires a theory that unifies the animate and inanimate. And so assembly theory is really basically saying that there is a fundamental physics of selection in the universe, and evolution, and that the universe in some sense is constructing itself. And where we start to see that physics be most prevalent is in the things that we want to call living things. Um, and I would separate, this is my physicist brain talking, but I tend to think, I like gravity as an analogy, for thinking about structures of theories of physics, because you asked about what a theory is and these kind of things. But like, we accept that gravitational physics is universal, but we don't use it to study inside the atomic nucleus. We do use it to study the large scale structure of the universe. We use it to study black holes. We use it to study planetary motion. And we recognize that, gravitational physics, there's the sort of space-time component, which is like the manifold that all of this physics operates in. And then there's massive bodies in that actually, cause the shape of space and time, and like their motion through, also causes the shape of space and time. So that's sort of the framing, right? And the way I think about life is, there's a universal physics. I used to talk about it more fundamentally in terms of information and causation. And now I really talk about it in terms of assembly and selection, because I think it's a better formal language. But, the same ideas and concepts still hold. There's a universal physics that exists in our universe, but the place where it's most prominent, just like gravity, you can study, in black holes and planets, you want to study the physics of information, or the physics of assembled selected objects, complex objects. Those are living things. So that's where we see that physics being
That's
its most
interesting.
prominent.
Okay.
And
Is
it's
that
so
because of the pressures that it puts at that sort of level of resolution? Like when you're mentioning this gravitational analogy, I'm thinking about subatomic nuclei. I'm thinking about even like whatever, like putting together my desk on in my office. That's something I recently did. Like the gravitational forces, I guess you could call them, are all the same. Me walking around my
it's a
office,
universal theory. It's just gravity is really weak. So like it doesn't
right?
matter. It's like it's the weakest of the four fundamental forces.
And
The
so it doesn't feel relevant at certain
That's
scales
right.
because
That's right.
it's just a, what would you call it? A constant at those
Yes.
scales. Okay.
Yeah, and it's too weak to have really any influence in, like, nuclear physics, for example. Like it's way over dominated by the other three forces. So so uh, so my point, on like this physics becoming dominant, it starts to take over in chemistry, but really chemistry transitions to what we would call life. because of this issue I was talking about before, where chemical space is so large, there are literally not enough resources and time in the entire universe to exhaust chemical space. And in fact, we've done some calculations that if you wanted to generate all of chemical space at about the complexity of RNA on a single planet, that planet would collapse into a black hole because there would be so much matter on it. So you just cannot exhaust all possible molecules. And so what happens is there's a boundary where not everything can be explored just randomly, and so choices have to be made. And if some constraints get built into the system that preserve some memory of those choices, a little bit anthropocentric language here, but that, like, selection is an active mechanism in assembly theory, then you start to build up specific structures at the exclusion of others, and that's what selection is. And so this physics doesn't really become really important until you have so many possibilities that ruling some out really changes the future evolution of a system. And also that memory is really necessary for those objects to exist. So, for example, like, everything in the biosphere is dependent on memory of the past existing in the present, because all of the sort of information and all of the constraints necessary to build computers and DNA molecules and ribosomes are, those constraints still exist in objects, and they keep getting remade. So, one of my favorite things is to think about the ribosome, which is, one of the oldest structures on the planet. So ribosome is an important molecule in every cell on the planet. It mediates translation, right, from DNA to protein. And ribosomes, they're as old as we know, like, we can date the history of life on Earth. So they've been on this planet for 3.8 billion years. And they have a half-life, I think, but don't quote me on this, but somebody might want to look it up and correct me, but maybe like 20 minutes, I think, is like an average lifetime in the
That feels
molecule.
reasonable for a ribosome. Yeah.
Something like that, right? It's a molecule. It's going to degrade.
Yeah.
So basically what's happening is, like, the information to construct that specific molecule has persisted on this planet for 3.8 billion years, and remade and remade and remade and remade that same structure. And because that structure can persist in time, because the information for it to exist keeps persisting in time, other things can exist. And so nothing on this planet would exist if ribosomes disappeared tomorrow, right? Like, everything would just decay over time. And also, like, that's just one example. There's like a million things like this on our planet. But just gives you kind of an idea about this fact that, like, everything in a biosphere is a constructed object and requires this history and memory. And these objects need to keep persisting together in order to keep existing at all. And they don't exist outside of those kind of spaces.
I've got a kind of philosophical question. Maybe it's philosophical, maybe it's fundamental. Maybe you're like, that's a dumb question, we're not going to talk about that. But,
Interesting questions are both.
it seems to be the case that assembly theory, and especially as formalized and utilizing these metrics, basically these formula, is something that can only exist, but I might be making a false claim here, post hoc, right? Like, you are making sense of the existing phenomena that we are studying. Is this also a predictive model?
Yeah, you can make predictions with it. So I just want to, and I'll talk about what those are in a minute, but you're making a really interesting point about sort of the foundations of the philosophy of science, and also in particular how physics has been constructed so far. So physics, like, the way that we write laws of physics right now is in terms of, like, a dynamical law, like, you think about the law of gravitation or law of motion or something like that, and an initial condition. So in a Newtonian worldview, you could put all the planets in the solar system in their positions, and then you have the dynamical law of, like, Newton's law of gravitation. You could run that system forward in time forever and be able to predict it forever. Obviously, that's not true in practice because of, like, three body effects and all this other kind of stuff. But in principle, and there's all kinds of issues with that. That's, like, some of them have to do with fine tuning of the initial conditions of the universe. Like, where did the initial state of the universe come from? You have to ask questions about where the laws of physics come from. And all of these things kind of introduce observers or some kind of information at the boundary of what you can understand in physics. And assembly theory does something really different, which is we do exactly this. We say, these structures exist. Let's build backward to ask how much causation, or, like, what kinds of features were necessary to create them out of the space of all the things that could have existed. Um, and so we start from the present, we work backward, and then we work forward again to talk about how much selection was necessary. It's a really different kind of paradigm than standard physics. And so right now, what we've done, the main sort of experimental proof of assembly theory is that's been in the published literature is this use of it as a biosignature. In terms of being able to say we can take a mass spec and we can go and take a sample and we can determine if its assembly is high enough to be considered living. That requires still a lot of work because we have to be able to predict why the boundary for complexity or assembly is where it is. We have experimentally verified about 15 for organic chemistry on Earth, but we don't know what it would be, say, on Titan or Enceladus, because the chemical space is different. Or for minerals, for example, like we were talking about rocks earlier, and could you directly compare their complexity to molecules? So one of the things that I've been working on quite a bit is trying to formalize the idea of a threshold or transition point in assembly theory that would tell you the boundary between non-life, quote unquote, and life. And actually, really, what we're doing is formalizing the origin of life transition with assembly theory. And I think what we'll be able to do is predict where that transition point is for any assembly space. So you'd be able to say where the origin of life, like what is the level of complexity origin of life happens, and what is the structure of systems that can transition across that boundary. So if we do that, then we have a theory that actually says something mathematically and also philosophically and deeply interesting about what the origin of life transition is, which to me is like the most incredibly exciting thing that could possibly happen in my career.
Yeah. It also takes this thing which is largely right now descriptive and largely, I guess, in some ways constrained by our N of one, and it allows it to be taken sort of out of the theoretical space and into the applied space, if we are looking at predicting or identifying life elsewhere in the
Right.
universe.
Yeah, and there's other things that we're working on too. So Lee's lab has a paper that I've been helping with trying that actually has mapped phylogenetic relationships without any genomic information, just using assembly spaces and mass spec. And that's incredibly powerful because I mentioned this issue of trying to trace back to the last universal common ancestor, like the earliest, sort of ancestor of all known life on Earth. We do it genomically right now, and we don't know how to push earlier than that. But if you imagine you have a method that allows you to talk about evolutionary relationships that are deeper than the genome, and you can extract it just from chemical data, like mass spectrometry data, it allows us to maybe start to build a bridge between the evolution of like what happened in geochemistry and what we see in life today, and actually like map that phylogeny. So that's another place where I think we'll be able to make some really concrete predictions, is in this gap region between prebiotic chemistry and the sort of last universal common ancestor. We have a lot of windows into that right now in my lab too, from some of the stuff that we're doing. So I think there's two sides there that we can tackle it. And the other one I'm really excited about is trying to predict alien biochemistries, which is, people have not really thought about aliens on other worlds as a predictive science, but I think it can become one where we could actually predict what kind of chemistries might be living chemistries on other worlds. And
Which then help us recognize it if and when we
yeah,
do detect it.
yeah,
It's
exactly.
interesting. It's like, in some ways, I can't help but feel like this very approach to physics is transcending the very category of what physics is versus what biology is. It's almost just like a different level of resolution to look at evolutionary processes, even beyond, like, there are constraints within biology. When we talk about evolution, we're specifically talking about genetic material very often. Historically, we were just talking about morphology, and now we're able to talk about genetic material. But it's a deeper layer, like you mentioned, to talk about something that was long, I think, the purview of biology.
Yeah. I mean, it's interesting because obviously, like, biology is life on Earth, but if you're
Mhm.
asking broader questions about the nature of life in the universe, it's, we might not even recognize it as quote unquote biology on another planet. It might look so radically different. And also, the origin of life is before biology, so like it can't have all the features biology has because it led to that system. So
Right, right. Even
yeah.
like the idea of chemistry, like not existing before biology, because I mean, I think did it? I don't know. Did biology come first?
Yeah,
Weird question.
well, it's funny because some of us that work in this field, like physicists thinking about the nature of life, think that, like usually people, when they do these sort of pie charts of disciplines, they have, physics as the biggest one, and then chemistry, and then biology, right?
Except
But
the
like,
mathematicians, they make math even bigger than
yeah,
physics.
math is better than physics. I'm a physicist.
Yeah.
So I started with the physics bubble. You can see my
Yeah.
ego coming through on that one. No, but I think my point is that actually I think life represents um, a broader and more interesting kind of physics than the physics that we have traditionally studied in physics departments. And so I view what current physics departments do as a subset of physics that life will enrich, which with a much much broader perspective on fundamental principles of what our universe is, how it works. And you can see that in, like we're talking about life and origins of life, but like people who study consciousness or artificial intelligence, like there's all these spaces opening up where it's just very clear that our current descriptions of reality are just not like, they're not the right ones for these problems. And they don't, in some ways they don't even fit like socially anymore. If you think about the time that Newton lived and the way that he wrote down laws of physics, they were very characteristic of his time and the mindset of the people living then about how reality should work. And now you have people claiming we don't have free will because the laws of physics say so. And I just think like these kind of statements are absolutely ridiculous.
I
Um,
would love to get a debate stage. I had Robert Sapolsky on the show recently talking
oh,
about that very
really?
thing. And I was like, okay, I hear your
Well,
arguments and I think they're coming from the right place, but I just fundamentally can't get on
well,
board with some of the things you're saying.
I find this so interesting because there's so many
Yeah.
people that reason based on physics as it is now without recognizing all the problems with it. And so they take physics as it exists now as ground truth. And it's really weird. I laughed and about this a little bit in my book about like when you're a physics student, you're taught to laugh at like the 1800s when people thought physics was complete and all this stuff was coming. But you walk around now and people think physics is complete. Like everybody thinks this. And it's just like mind boggling to me that like for some people, there's no room in their brain for new fundamental laws of physics to be discovered that might
Right.
totally change the way that we think about things.
Right. And
Um,
that's such I feel like that, coming back from the psychology perspective, it's part of what it means to be a human being. Like there is a security in feeling like the ground is solid beneath our feet.
yeah,
And if we felt all of the cracks in the ground, then we'd be like readily aware of how easily we could fall through them.
yeah,
And of course, for some people, for their career, the interest is in seeking out those cracks and,
right. I was
propelling down into them. And for other people, they're like, nope, nope.
I was thinking I must have some kind of pathology because I want to stand on all the cracks.
It is funny that there is something very uncomfortable about the unknown. There's something very uncomfortable about a lack of categorization, a lack of labeling, a lack of being able to put something into a box. And even this very approach, assembly theory, is an attempt to make sense of something that right
Yeah,
now is not well
right.
sensed.
Yeah,
um, but yeah, it's that weird paradox of like working to operationalize, working to have a deeper understanding of something, and yet being comfortable saying part of this process is that there are things we don't know and probably won't know. Like, doesn't mean they're unknowable. That's another philosophical
right,
debate that we don't have, but just
right.
like probably won't know within the time scale that we have
Yeah.
available to us.
Well, every answer opens up like, hundreds of questions. So I think that's also, something about the expanding frontier of science. It's not, I personally feel like there is no end to the sort of questions that we'll be asking or, yeah.
Yeah, and there's something deeply exciting about that to me, and I assume to you and to your graduate students
Yeah.
and to the people who attend, who read your book and attend your lectures. But I think it's also can be terrifying, like existentially terrifying to a lot of people to
Yeah.
think that we don't know so much.
Yeah, I remember when I started studying physics, and I told you I was at community college. I went to this party, and I was talking with one of my friends there about this stuff, and he was just like, he was one of those existentially terrified people. He's like, I need you to stop talking, Sarah. Like this is too much for me. I can't handle this. And I was like so naive. I was just like, this stuff is amazing. What are you talking about?
And he's like, I'm falling in the cracks.
Yeah, yeah.
Be careful. I don't want to go down there with you right now.
Yeah, I know.
Oh
I
yeah,
know not to be like in the deepest. I just thrive there. I love being in the swimming in the unknown, and I love thinking abstractly about how to understand it.
I love that because in talking about the nature of life and the nature of, in some ways, existence, we are talking about the nature of reality as well. And there is this sort of parallel here between this very formalized, scientific, even mathematic and quantifiable approach to looking at assembly theory, to looking at these indices, but also this more, I guess, philosophical, ineffable conversation about who we are, what our place is, whether we feel groundless, whether we feel deeply connected, and the confidence that comes from knowing, the discomfort that comes from unknowing or not knowing, but the freedom that comes from that. And I think that that takes us to this interesting place where we're talking about the fundamental nature of science as a process and the sort of general misunderstanding that science is not about let's figure stuff out and then sit on it for the rest of our lives and teach it as a series of stuff we know. Science is a function of constantly evolving our views and our opinions, even if it means going into really, really uncomfortable territory where we have to kind of sit with the question of like, what if I don't know anything about anything? And this is a new way to start to learn. There's something very special, I think, about people who choose to engage with science in that way. And it's sort of in some ways flies in the face of the way that I think politically, like there's no political expediency in thinking scientifically. It's sort of the opposite of the way that we like to talk in the political arenas, which is all about being sure, not changing our minds, being confident in our views. And I think that it's a bit dangerous for the populace. And if we could, I don't know, if we could use a little bit more of that scientific thinking, a little more of that, I'm not sure, but that's okay.
Yeah,
Yeah,
no,
it could benefit us all.
I totally agree. I think about this quite a lot. So one of the reasons that I'm really motivated to do like public intellectual work, like, because I don't really view myself as a science communicator. I really value people that do science communication, but for me, I feel like it's really important to like be doing your most cutting edge stuff in public, getting the public thinking about it at the same time you are. Um, and realizing that like we're constantly in failure mode and we're really trying to figure it out and how hard it is, but also because these questions are unknown, there's like a chance for a dialogue about like the nature of life, for example, is like I don't think anyone, any one person should decide how we want to think about what life is. Right. And like, obviously, like, there's a reality out there that we can test scientifically, but how we talk about the theories we build and the experiments we're doing does matter because it structures how we feel about ourselves and like how we envision our future. And so I really feel a lot of responsibility in some sense to really try to get the ideas out there and like socialize them and see how like culturally they resonate or not, and who's thinking about these things, and in what ways do we need to sort of change the nature of the discourse. And so I think those kind of things are really important. And the other thing about scientific theories that is really interesting is like they really do shape the future. I really studying the physics of life, like I think the future is open, and we have a lot of agency for shaping the way the future looks. And so I think it's really important that we really think about the science we're doing and like what kind of future and vision for the future does it build. And obviously like there's no like utopias are like the scariest thing ever, so like there's no scenario out there, but like trying to build optimistic things and involve a lot of people in the dialogue is really critically important to trying to build a future that we want to be in, because we'll be there eventually.
Yeah, I mean, here. I'm curious, Sarah. I've already kept you like longer than I intended to. Obviously, there's like a million things we did not get into about your book, but is there anything that you feel like I don't know, like we absolutely need to touch on before we wrap up? Because I wouldn't want it to go unspoken.
Yeah. I don't know. Like Yeah, no, I think I'm okay. This was fun. Because as you're saying, like if I start like that one thing flood in my brain, like a million other ones do too. So
then it just all follows and
yeah,
follows. So.
there's not one that's standing out that's like, oh my God.
Oh, good. So we have sort of introduced the concept at a level that hopefully was accessible here on the show, so that those who, and I hope I'm talking to you, everybody, those who are interested in digging a little bit deeper. When is the book of? I've got your galley here, so let me see. The book published date, is it on here? Oh, August 6th. Awesome. So it will be already available as this show goes to air. And yeah, I hope everybody has a chance to pick it up. It's called Life as No One Knows It: The Physics of Life's Emergence by, I know you hate it when I do this, but I'm going to do this, Dr. Sara Imari Walker. Sara, thank you so much for being here with us.
Thanks for having me. It was really fun.
Of course, and everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.